All right, let's see how we are doing. We are doing 6 out of 19. I think I'll wait for everyone else to show up. Okay, while I'm sort of waiting for everyone else to filter their way through, let me add that if you haven't seen the announcement, I have pushed back the date on which you need to upload code. That does not push back the date when you have to upload the presentation, but the code upload is moved back because it was sort of unclear to a lot of folks what exactly you're uploading and why, that kind of thing. So code upload been delayed. Presentations are still due to be uploaded tonight at the end of the day by midnight. And again, just to remind you of how that'll work, well, I guess I'll go over this in a moment. So we will get back to that question in just a moment. Okay, well, I think it is time to begin. Let me share my screen and we will be good to go. Wait, no, I think I did the wrong thing. Hold on. There we go. All right. Well, in the last couple of lectures, we've been talking about dependent types as an approach for writing verified programs. In particular, we've discussed how this is an approach that allows you to write a single program that both contains an actual implementation of some computation, but also computes a proof that that computation is correct. So it's this kind of mixed environment. Instead of having this methodology where you first write the code and then later you verify that the code is correct, it instead is an environment where you develop the code and the proof that the code is correct simultaneously, possibly leveraging each other. And that allows you to write more scalable systems, verify them more simply. And in some sense, if the goal is actually to produce a piece of verified code, as opposed to verify a piece of existing code, this approach makes a lot of sense. And in fact, what software verification people have found over the last couple of years is that it's a lot easier to write code with an architecture that allows it to later be verified than to take a piece of existing code and attempt to verify it without changing it. And so in dependent types, you kind of take this to its logical conclusion and you say, well, the code and the verification of that code will actually be the same thing. There'll be one piece of code that kind of does both. And today I wanted to take a look at a research paper. Hopefully all y'all have taken a look at it before this class, at least reading the first couple of sections. This project was developed chiefly by students of Adam Chapala. Adam's been a researcher in software verification, specifically in this dependent type style, for a long time. He's done a lot of amazing research showing how to take, specifically often looking at low-level code and showing how to combine a high-level structure and high-level verification with low-level performance, low-level code. And this is a great example of that. It's a project to write a verified implementation of certain cryptography primitives, and write that verified implementation in such a way that it's easy to maintain. The code is high level, it's relatively easy to understand and to verify, and yet at the same time, produce low-level C code that is as fast as anything in the state of the art. So that's what I'll be talking about today. These are mostly my slides, but I've significantly leveraged some slides that Adam provided me and also some hints from him about what he thinks are the most important parts of this implementation of this work. Before I get to that, let me just give you those details I promised on the class projects. So as you know, the final presentations are due tonight. I'm asking you to record those presentations and then upload them on Canvas. I know some folks have had some difficulty with that because it turns out that Canvas is kind of a mess. But I think I've enabled some more features that make it easy. I hope so. I don't know. There is an option for you to put in a URL. So if you can't figure out how to upload it to Canvas, please upload it to YouTube instead and put that URL in. You know, that's just as good. Also, keep in mind, you probably want to budget a little bit of time for handling Canvas's nonsense, and also uploading a presentation can take a while as well. So don't start uploading at 11:59. What we'll be doing with these presentations after you record and upload them, I will be posting these presentations so that all of you can see them. And the goal of this is that all of you can watch each other's presentations, like we might have done in class if we had more time, and also if weirdness regarding coronavirus hadn't happened. And I am asking you to watch all the other presentations and write a question for each of them. So I'll put up a Google form where you can, or actually, sorry, a Canvas form where you can submit these questions. So I'm asking you to ask one question for every other presentation in the class. And then I will collate these questions that were asked of your presentation, and I'll ask you to provide written answers for them. And if you look on the course website, you'll see the schedule for that. Basically, you have until Tuesday to watch the presentations. And then once you have watched the presentations, you will have a couple of more days to, I think by Thursday, to answer the written questions. So any questions about the class project presentation? Skylar, go ahead.
So for turning in our answers, do we each individually have to turn in the answers for a group project, or is it similar to how turning in the presentation worked?
I'm trying to keep it the same as the presentation. So if you have a group presentation, then the questions are asked of your presentation, and you can work together on the answers. It'll be a group submission like the others. If like one of the milestones I forget to do that, then just ping me.
Okay.
Other questions? Okay, great. So that's how we're doing the final presentations. I've also asked you to upload the code for your final project. I think what exactly to do and what to upload is unclear to a lot of people, so I pushed back the deadline for that till Tuesday. Basically, I'm asking you to submit all of the code that you wrote for the project. So if you are doing the solo project, the alternative assignment, then I'm asking you to upload all the code pertaining to your interpreter and your verification condition generator, the parser, and the quicksort implementation, and other sample programs you've written. And so we'll look at your code. We'll see that roughly speaking, you more or less implement things like we can figure out roughly speaking that you've implemented things. We're basically checking that you actually did the project, didn't just make a presentation claiming it worked. We'll attempt to compile your project and verify some stuff on it. So, see if we can verify some false things. That'd be fun if we succeed. I'm also asking you to include a README with your upload, just locating where the various things are in the code. So I'm basically asking you to say something like, the parser is located in, something, 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 parser.java, and it's based on an Antler file located in something, 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 grammar.g, and et cetera, et cetera. So basically for each component, sort of roughly walk us through where the various pieces of code are located. And we'll be taking a look at that. If you're doing a group project, it's a little tougher to answer the question of like what exactly you should upload, but you should think about your project. Basically, we're looking for you to upload whatever it is that you did, whatever's relevant to your group project. So this might be a diff, it might be a branch you submit to an existing project, it might be a set of experiments you've run, it might be, well, it might be any of these things. So we're asking you to submit that, any evaluation scripts you have, any evaluation data that you produce. So we will mostly not be running the group projects because it might not be clear how to do that. That's actually been one of the challenges for some of the group projects. But we will be sort of looking over your code to just see that it basically corresponds to what you have in the final presentation. Tanmay?
Yeah, what about the dependencies like Antler and Z3?
We'll have Z3 and we'll have Antler on our machine. If you have anything super weird, like compiling Java code is awful. So if you have anything super weird, then let us know in the README. But if it's just like Antler and Z3, you know, we'll have Antler and Z3 around. Any specific dependencies you're worried about?
No, that's
Awesome. Any other questions about the class project, how the end of this course will go, the presentations, what to expect, panic about grades, anything?
Joke's on you, I'm always panicking about my grades.
Yeah, you know, if you're always panicking, then when truly scary things happen, you're already prepared. I know a few people like that. They've been loving this crisis. Okay, if there aren't any further questions, anyone wants to ask in class, I will add that you can always email me and Manasij, and we'll try to clarify whatever we can. I'm sure you're all feverishly working on fixing the last remaining bugs in your code. Okay, in that case, let's talk a little bit about the Fiat cryptography project. Let me start by telling you a little bit about cryptography, because you've probably heard a lot about it, but I don't know whether y'all's crypto background, how your crypto background actually is. So here's like the 5-minute, really bad, do not take this to the bank explanation of cryptography. Roughly speaking, you use the internet, and when you use the internet, your browser connects to some kind of web server, and it might, you know, send some kind of request. And so one type of request that your browser can send is what's called a GET request, and that corresponds basically to a read of some web page. So here I'm pretending that maybe you're accessing your account on some website, like maybe your bank, I don't know, that'd be bad though. And you could say, I'd like to read the information about my account, get the web page that describes, you know, your balance and whatever. And when your browser does this, it needs to identify somehow that it is you and not some other person. You can't look at other people's accounts. So to do this, it passes along what's called a cookie. No one knows why it is called a cookie, but it is called a cookie, and it usually contains some kind of opaque identifier for you. Generally, the way this works, you log into a web page, you send the web page your username and your password. The web page then generates a new identifier for your login. It gives that identifier to your browser. Then the browser hands it back to the server every time it has a further query to make. And that's how the server knows that you are you. On the server side, it remembers that this ID corresponds to this login. That way, you're not sending your username and password across the internet all the time, but you can still authenticate your browser as you. So the system is great. This allows, you know, your browser to get whatever kind of private information about you, prevents, you know, other people from seeing your data. But one concern is that you and the browser might not be the only people on this connection. In fact, there might be someone else at, for example, your coffee shop or within your home network that can also see all of the messages you send back and forth between your browser and the server. There's actually a lot of entities that might be like this. It could be other patrons at like a weird early 2000s coffee shop that still doesn't have encrypted Wi-Fi. but it could also be people on your local area network. It could be people within the university. It could be your internet service provider like Comcast. It could be the backbone internet provider like L3. It could be whichever country your connection happens to pass through that maybe you don't trust. It could be the US spy agencies or the spy agencies of those countries. And of course, it could be anyone on the other side of the connection, Cloudflare or someone that the business contracts with to pass through connections. So all of these entities, if any one of them is bad, it could see the message being sent. And that message includes information that authenticates your browser as you. So here I've got this man in hat from XKCD, and he has eavesdropped on the connection and determined the token that your browser uses to authenticate itself with your bank. And because that knowledge of that token is what makes your browser represent you, and since now Man in Hat has the token, he can also send requests to the bank using that same token to authenticate this request as coming from you, except now he's no longer doing a read, he's doing, for example, a transfer on your bank to himself. No actual bank works this way, this would be absurd, but you can get the general idea. You probably can't initiate a transfer in this way, but you can initiate all sorts of other transactions with the various accounts you have online. So there's a real worry that, especially for an important connection or for especially vulnerable individuals, maybe you think, dissidents in some country, you would be particularly worried about someone eavesdropping on the connection and initiating requests or even just reading information that they shouldn't have access to. You might not want someone transferring money out of your bank account, but if the money in your bank account is not that big, you could still be quite clearly embarrassed by other people reading your chats or your emails. So we'd like to prevent this big idea, and to prevent this big idea, we want to sever this connection where someone on this line can read the contents of your communications with another server. So that's the idea. We'd like to encrypt all the network traffic. If the network traffic is encrypted, then no one can eavesdrop on the connection. Even if they do, they'll only hear encrypted traffic, which will make no sense and will not tell them the token, and it will not allow them to make their own requests. There's a lot of asterisks in that sentence. I didn't verbally put them in, but they're all over the place. But if you do it right, this is the general idea. So here's how encryption works. The idea is that if you know the encryption key, then you can read encrypted data and figure out what it actually means. If you don't know the encryption key, then it's just some gobbledygook. And on the internet, this is done using a protocol called transport layer security. If you've used the sockets API, it's basically like sockets, but everything you send across it is encrypted. And if you've seen HTTPS:// in your browser, that means that the browser is communicating to the server using TLS to encrypt the connection. So there's kind of various versions of this. People keep adding more features to it, tweaking the security parameters, and also adding new ways of encrypting various data. So questions about this general setup of encrypted traffic on the internet. I can't answer everything about it, but this is very relevant background to implementing cryptography. Great. And before I go on, who here has taken a course in cryptography or something along those lines? Network security. You can do the raise hand thing. Okay, I'm getting limited uptake on prior cryptography knowledge, which is good. Then that means I'll make sure to take more breaks as I'm going through this background information. You can put y'all's hands down. Okay, so let me tell you then a little bit about how encryption works. We have this idea that we want to take a message and turn it into some encrypted version of the message that you can't read without having access to the secret key. Well, if you want to set this up, then there's going to be some kind of process in the middle that we call a cipher that translates the message into the encrypted version of the message. And this cipher takes this additional input, which is the secret key. And so somehow we need to set it up so that the two parties to a connection both know the secret key, so that they both know what messages they're sending back and forth, but no one else does. And this is back when cryptography was first invented back in the ancient times. This was a pretty simple procedure to come up with. The king or whoever would agree on a secret key with all his spies. I assume the spy master agreed with all the spies on a secret key, or maybe with a different secret key for each spy. They met up ahead of time. There's only, they knew who each other were, so it makes sense to just have this expensive key arrangement protocol. And in fact, fun story, during World War II, I believe the US would ship these big, like, physical, I think they were magnetic tapes, I'm not 100% sure, that contained the secret keys that would be used for encrypted telegrams between the US and Britain. So this was a physical object you'd have to, ship across the ocean at great expense. But about 50 years ago now, I think that's about right, a different method was invented for coming up with this secret key. And it's quite clever. The idea is called key exchange. So the goal here is to have two parties, the browser and the server, for example, agree on a key without having to meet each other ahead of time or have any other kind of prearranged setup. So here's the key ingredients to a key exchange algorithm. Key exchange starts by having some public information, which we call a base, or sometimes we call it a point, or sometimes we call it a generator. Doesn't matter, I'm gonna call it X. There's some public information that presumably not just the two parties to the communication agree on, but also everyone knows. And these are published in government standards, for example, like the NIST FIPS standards. And then there's also some space, some large collection of private functions that we could apply to the base. So I'm just going to call them F, G, H, etc. And a key guarantee here is that these functions are commutative. So if you have any two functions from the set, like F and G, then F of G of X should be equal to G of F of X. So this is kind of a weird, pretty abstract setup, but there's a lot of such big collections of functions. For example, multiplying by constants. We know that multiplying by constants or raising numbers to powers, those commute. So that's one collection of such commutative private functions, commutative spaces of possible private functions. And then here's how key exchange will work. First, we have our two parties, the browser and the server. And each of them will pick their own secret from this large collection of possible secrets, more or less at random, lots of asterisks. So let's say the browser picks F, the server picks G. Now they don't tell anyone. What they do, however, tell each other is that function applied to the base. So the browser will pick F, it'll compute F of X, and then it'll tell F of X to the server. And since we're assuming the connection between them might be eavesdropped, any possible attacker, basically anyone who wants to, let's assume, can learn F of X. And likewise, the server computes G of X and says that to the browser. So F of X and G of X are public information. Those are exchanged between the two parties. And then each will apply their secret function to the result. So the browser has now received G of X from the server, and then it applies F to that value. So the browser's now computed F of G of X. The server has computed G of F of X. And because F and G are guaranteed to be commutative, these two values are known to be equal. So the browser and the server have each come up with the same value, F of G of X, but the only stuff they publicized was F of X and G of X. So as long as it is difficult to go from F of X and X to F, and it turns out there are many ways you can set this up, any possible attacker, anyone eavesdropping on the connection, only knows these useless values like F of X and G of X, but can't backtrack from those to learn F and G, which he or she would need to compute f of x, and g of x themselves. So this is the general scheme of key exchange, kind of presented with only the key steps. So let me take any questions on this basic idea. No questions, huh? This is like one of the coolest, deepest ideas in computer science. I think they won a Turing Award a few years ago. Calvin?
So I've heard before the term like hidden subgroup problem that describes like a lot of these, like the elliptic curve algorithms and RSA algorithms and such. Is that related to this concept, or is it like a different kind of concept, or?
That's related to this concept. It's due to this. There's sort of two, well, I guess there's sort of three assumptions that I've had when I present. I've tried to present this kind of as abstractly as possible. This is the core idea with these commutative functions. Making it work in practice, first of all, means that you can't go from f of x to f. And secondly, that there are, in fact, lots and lots of these private functions, so that you can pick one at random. And in fact, that if you pick one at random, or even if you do a relatively bad job picking it, you still have this property that you can't backtrack from f of x to f. So the space of this set of private functions, you got to choose that carefully. If you do a bad job, it'll turn out that, for example, it might turn out that like half of the private functions, you can't go from f of x to f, but in the other half, you somehow can, and that'd be bad. Or, these functions could be of the form that you can invert them, though I don't mean inverting the function going from f of x to x. I mean going from f of x to f, which is kind of this weird thing. So the hidden subgroup problem, that's one way in which this sort of thing can break. Actually, in the sort of intervening 50 odd years since Merkle and Diffie and Hellman came up with this algorithm, there have been all sorts of different tricks that have been found, ways that you can basically implement this while leaving a loophole that someone else can get in through. Skylar?
So just to clarify, RSA is like an example of one of these sorts of algorithms, right?
RSA is something related, but actually not that related and different. RSA is an encryption algorithm. So it has these private and public keys. And if you know the private key, the public key of some other party, you can encrypt something that only they can read. This is a more specific notion. It's not about encrypting data itself. It's just coming up with a key that is then used for symmetric encryption. So here, both parties end up with the same secret, f of g of x or g of f of x, and we know those two are equal. In RSA, it's a sort of more advanced, more complicated form of encryption, where two parties don't actually need the same secret key to communicate at all, which, by the way, sounds a lot better. And the reason we don't use that for internet communications is that it is orders of magnitude slower than what we call symmetric, or both parties have the same key encryption. So what internet connections actually do is they use this algorithm to come up with a key that both parties know. And then once both parties have the same key, they could use these blazingly fast implemented in hardware algorithms like AES to do the actual encryption. So some of the same mathematical mechanisms come up in both. You can do RSA with arithmetic modulo large primes, and Diffie-Hellman key exchange also is often arithmetic modulo large primes, but the actual goal of the algorithm is different in that way. Does that help?
Yes, yeah, it does. Thanks.
Awesome. And I think, Oliver, you have your hands up as well.
Yeah, I'm still a little bit confused. Which x's are the same x? Because there was the public base and then the message, and I wasn't sure where the message was.
Again, this step is not the actual encryption step.
Oh, this is just getting the key. Gotcha.
This is just getting a single shared key. So there's no messages being sent. I mean, sorry, there's definitely messages being sent between the two, but the actual content of your internet connection, that's not involved here at all.
Gotcha.
All of this happens.
They are all the same
any
x.
of the other steps. Yep.
And then where does the server get the G again?
It makes it up. So for example, in the specific crypto systems we'll be talking a little more about as we go through these slides, this set of private functions is identified by a 256-bit number. And so the server makes up 256 random bits, and that is its G. And the browser does the same thing on its machine, and now you have an F and a G.
And it generates them in such a way that they are inverses always?
Again, they're not inverses. The guarantee is no matter what numbers you generate, the functions that those numbers represent always commute. So this is
Oh, it's
all
commutative.
F
Yeah.
and G is what I mean by
Oh, it's commutative. Okay.
yeah.
Thank
So you can see that setting this up suddenly, the core idea hopefully is kind of explicable. This sort of commutativity and this thing with the private keys and the F of G of X. Actually setting this up though, that's where all the difficulty lies.
Yeah, I can understand how it works, just not how you would even set it up in the first place.
Yeah, and in fact, sort of a funny story about how this was invented. You may have noticed that I called it Diffie-Hellman key exchange and then put Diffie and Hellman and this other dude on the slides. I was hoping someone would ask what Merkel's deal was and like why he didn't do a good enough job to get on the name of this. And the answer is that he was working for a spy agency, so he never published.
Wow.
He invented it first, but unlike Diffie and Hellman, he kept it secret so the British government could use this idea. And this goes back to some even earlier work that hypothesized the possibility of key exchange. Diffie and Hellman, if I remember my history correctly, their specific accomplishment was not just coming up with key exchange so much as actually introducing a practical example of how key exchange could work. And honestly, I don't remember the history well enough to tell you exactly the subtleties here, but that's roughly speaking what is going on. Okay, so let's move on from the high level mathematical, or even like, man, I don't know what to call this, just like broad speaking computing idea of this key exchange and look at some practical implementation details. We need to pick all this stuff. The public base, the set of private functions, they need to be commutative somehow. How do we do that? Well, it turns out that the mathematical structure that we're looking for here is a thing called a group of functions, and subtleties elided. But broadly speaking, this set of functions follows a mathematical structure called a group. And you need to decide that group in advance, but that group, which is the set of all of these functions, that's usually made public. And again, it's usually published by like large government agencies. And on the web today, there's two popular classes of such private functions. One is raising numbers to integer powers modulo large primes. So your base might be some number like 3, and your functions might be raise the input to the power of 17 modulo 97 or some other large prime. I hope 97 is a prime. And of course, in reality, the primes are enormous, much bigger than 97, if that is a prime, which I'm not sure. So that's one option. That's also, of course, the sort of operations used in RSA, as mentioned by Skylar. And those are sort of the more traditional implementation. But these days, the option that's becoming more popular for a variety of reasons is what is called multiplication on elliptic curves modulo large primes. So we've got this large primes thing, they're everywhere, but we also have this weird elliptic curves thing. I should also note these aren't in principle the only options. People have looked at other examples of these groups. It's just that for a variety of reasons, both simplicity of analysis and depth of mathematical knowledge, and also experience with actual implementations, these are the ones that are most commonly used. And in fact, if you go into your browser, let me see if I can figure out how to do this in Safari. If you go into your browser, you should be able to find out the algorithm used. Maybe I can't easily figure out how to do this in Safari, but your browser and web server, if you run one, will tell you this like incredibly long string of letters about what cryptography it's using. And it'll usually either say something like DHE, which would probably mean this for key exchange, or ECDHE, which would mean that. So we've got this elliptic curves multiplication nonsense. Let me tell you a little bit about what exactly an elliptic curve is. An elliptic curve, hilariously enough, is this sort of weird mathematical function. It's defined as y squared equals, and then some cubic function. Usually you write it in this form so that it has two parameters, a and b, but generally speaking, just some polynomial of degree 3 in x. And so here are some pictures of elliptic curves. If you just draw them, here's one, here is another. And a weird fact that has been known since the Renaissance is that there is this operation you can do which takes individual points on an elliptic curve and produces new points on the elliptic curve. And so here's the operation. You take 2 points on the elliptic curve, you draw a line through them. That line meets the elliptic curve at some third point, and there's some asterisks there, but you can work them all out. And then if you take that point and just reflect it across the x-axis, yes, it's unclear how you'd come up with this, but just work with me. Now you get some third point. And if these 2 points are called A and B, we call this point A plus B. Okay, so here's this is like a weird thing that you might do if, I don't know what else there was to do during the Renaissance. So I guess that's the explanation. But it turns out that this operation has the intriguing property that, first of all, it's commutative. And you can tell it's commutative because if you draw the line from A to B, that's the same line as if you draw a line from B to A. It also has inverses. So it turns out that this point and this point are inverses in a certain way, where you treat, where you imagine there to be a point at infinity, which you call the 0 point of the addition. And therefore, these form a group. This operation is commutative, it's associative, it forms this mathematical structure called a group. So that's a weird mathematical fact. And it turns out that for whatever reason, this weird mathematical fact is the basis for approximately half of cryptography on the internet today. So on computers, instead of doing this for curves just over real numbers in general, we also treat all the arithmetic going on here, the squaring, the cubing, the coefficients, and so on, modulo some large prime p. And if you standardize the choice of curve and the choice of modulus, and you also fix that base x, which is going to represent some initial starter point on the curve, then that specifies a crypto system that you can use for key exchange on the internet. And I can actually give you some concrete examples of those. This is a very popular curve. It's used on, I think, about half of elliptic curve connections. I'm not 100% whether that's up to date or not. This curve is called P256. It's called that because the federal government put together a standard and they had curves for primes where the leading digit was 2 to the 256 and also like 244 and 192 and a bunch of other different sizes for different basically amounts of computation you'd be willing to spend. So here's the particular curve. It's exactly that format that we talked about earlier. Y squared equals x cubed minus 3x plus a, where a is this enormous 256-bit constant. And then here is the prime number that you treat everything in terms of. You can see that this prime number has only a few, it's very close to being 2 to some power. Of course, can't just be 2 to some power because that's not prime, but it's pretty close. And in fact, the powers of the the exponents in the powers of 2 that differ from 0 are also pretty regular. So as you can imagine, coming up with this curve required looking for a prime with this particularly nice form. So that's what a standard crypto system might look like. It's this curve, it's this prime, and it's also some enormous constant to be the base number. Another curve that is quite common today is called curve 25519. It's called 25519 because the prime is 2 to the 255 minus 19. And the actual curve is in a slightly different format, but you can see it here. One of the reasons this curve became popular is because after the Snowden leaks, people were fairly worried about how exactly the government had chosen these constants A and B. Did they have some secret knowledge? Did they pick them in such a way that allowed the government to read your messages using mathematics and cryptography that no one else in the world knew? So we instead just trusted this one guy called Daniel Bernstein, who came up with a curve where the actual primes and also all of the constants are appealingly small, making it difficult to believe that there was something up his sleeve. Also, the cryptographer himself did not work for a government agency, so that was also a point in sort of its favor. So this is why this curve became popular. It's appealingly easy to describe, and it turns out to also, because of this extremely short representation, be very easy and very efficient to implement in hardware. Daniel Bernstein is known for tricks like this. Questions about elliptic curves and basically implementing crypto systems at a high level? Skylar, I saw you had your hand up, so if that's still relevant, go ahead.
I was going to ask why it was called 25519, and then I figured it out. So,
it took me a very long time to figure out that that's why it was called that. Yeah, it's an appealingly simple name too. Any other questions? Okay. So now we've discussed this high level idea of key exchange. We've lowered it one level. We've talked about elliptic curves, which provide this set of functions that are commutative, and it happens to be the case that they also do not, they're also hard to invert in that way that I discussed earlier. So these kinds of curves, modulo these primes, these are the set of functions the group used for a lot of cryptography on the internet today. So how would you go about implementing this? Well, what you need is fast arithmetic modulo P, and P is usually big. In that previous example, they were 2 to the 256 and 2 to the 255. Your hardware does not have native arithmetic for integers that big. So you need to implement this in software somehow. Furthermore, you need it to be extremely fast because this is the very first thing that happens on an internet connection. The longer this takes, the longer you delay everything else that's going on that connection. So this isn't happening message by message. It's not like it needs to be fast because your computer would use too much CPU. On the contrary, this is a latency bottleneck. The slower this goes, the longer it'll take to establish a connection. So you want this to be as fast as possible. Furthermore, on the server side, not your browser, you want the server to serve as many connections as possible because the company wants to have as few servers as possible because they cost money. So you want it to be low, and you want it to have high throughput as well. So low latency, high throughput, pretty tough demands. Furthermore, there's some security properties that it needs to satisfy. Basically, the implementation has to be what's called constant time, which means that no matter what two numbers you are multiplying, you have to get the answer in the same amount of time. So if you're multiplying 1 by 1, that has to take just as long as if you're multiplying some crazy 256-bit number by some crazy other 256-bit number. So this security consideration, which is just related to this idea of not leaking information about the secrets in the time that it takes to do operations. This security constraint means that you can't use general purpose, arbitrary size arithmetic libraries. And of course, these additional concerns mean that not only can you not use those libraries, even if you could, you wouldn't want to because they're way too slow. You need this to be as fast as possible. You're probably going to write it in C or assembler. You're probably going to want to make use of all the features of the hardware available. There's going to be vectorization. It's going to be super crazy, super hard code. So what you're going to do is, instead of representing numbers just as arbitrary size integers, you're going to represent them as vectors of machine integers. So some 255-bit number that can be represented by, for example, 4 64-bit numbers. This is just one of many representations. If you've looked at the paper, you know that we often choose different exponents here for a variety of reasons to implement what's called unsaturated arithmetic. But broadly speaking, the idea is each individual number is going to be represented by some number, maybe 4, maybe 6, maybe 10 ints on the machine. So the implementation is going to work kind of like this. What you're doing most of the time is you're multiplying these large numbers. Adding them, of course, is just adding with carry, but multiplying is pretty tricky. So suppose we got 2 of these numbers. I've got X and I've got Y, and both of them are represented as 4 machine integers. Now, to multiply these, we can think of this as the digits of a number in base 256. And then we can implement multiplication using the same algorithm that you learned in high school. I don't know if it's the same algorithm kids learn now in high school, but when I was in high school, or actually like middle school, elementary school, wherever you learn how to multiply. So the multiplication goes like this. First, you start with the least significant digit, which inconveniently I've written on the left here. And you have this product that is going to be your ones term. Then you have 2 different things that you add up for your tens term, which is that one. And then for the, and then for the hundreds term, you have these options and so on and so forth. So you can build out the sequence of numbers. You have in this case, a ones term, a 2 to the 64, a 2 to the 128, and a 2 to the 192 term. And now we're going to continue. The next thing that we're going to look at is we're going to look at multiplying this by this. Remember, when you do sort of schoolyard arithmetic, you get this kind of trapezoid shape for the set of numbers that you're summing. So the next, we're going to get this product, which is going to have a 2 to the 256 place for it. Except that we're doing all of this arithmetic modulo, for example, 2 to the 56 minus 19. I know that in 25519, it is, of course, 255 minus 19. So that's kind of embarrassing, but bear with me here. Let's assume that for whatever reason, you're doing this in 256 minus 19 itself. Not sure if that's a prime, probably not. Again, sorry. In this prime, 2 to the 256 is actually equal to 19. So we can take these things, which have a 2 to the 256 multiplying them, and actually move them to the ones place with a 19 in front of them. And then, of course, we'll also have a 2 to the 256 plus 64, 310 or something like that. Whatever is one digit even higher than that. But these all stack back into the existing columns that we have. So basically now we have this multiplication all done. We've just shifted some of the things over back into the ones and tens and hundreds digit. And now we're going to just add down the columns to compute the new coefficients of XY. So that addition, there might be some carrying going on. There might be some other stuff going on, but broadly speaking, that's what we end up doing here. So that's this core multiplication algorithm that you need to implement, and you need to implement blazingly fast if you want to get a good crypto system implementation for internet cryptography. So questions about this, this whole kind of crazy scheme where we're doing crypto with elliptic curves and weird stuff and multiplying big integers, and it all has to be fast. All right, raise your hand if you remember multiplying big numbers like this in elementary school or wherever we learned to do this. Awesome. It's good to know people know how to multiply. And it turns out your computer spends just as much time doing it the sort of boring old-fashioned way that you learned in school. Matthew, is that a real question?
Nope.
No. Okay, you just wanted to make it clear that you knew how to multiply numbers. That is good. Don't forget. Okay, so we've covered the challenges. So we just need to implement this, and that code just needs to be very good. So doesn't sound too hard. Here's the issue. You don't just implement this stuff once. There's a bunch of different tricks that you might want to apply to speed this process up. There's a crazy number of different algorithms. Then those algorithms are going to depend on, we're going to want to specialize them. You want the code to be as fast as possible for the particular elliptic curve, which really means for the particular prime that you need to do the arithmetic on. And then you're going to want to use all the hardware tricks available on your particular machine. Does your machine have 64-bit arithmetic? Does it have 128-bit arithmetic, which almost no machines do, but could in principle exist? Do you have vector units? Do you not have vector units? Do you have, what's the speed of the multiply with carry? That kind of thing. So it turns out you actually need not just one implementation of this, but k times n times m implementations of this, which, given the diversity of computing in general, and also with the huge scope of devices you want to access the internet, not just servers and desktops, but also like fridges now and light bulbs for some reason. It's a crazy amount of implementation effort that has to go on. So you have to do a lot of these implementations. All of them have to be very good. And as a result, you are always having expert cryptographers implement known algorithms for existing primes on new machines, or algorithms for new primes on existing machines. Or there's just a lot of effort, and a lot of effort by extremely specialized people with a lot of expertise. So it's expensive, and not enough of it gets done. Furthermore, even experts sometimes make mistakes. So because of that, you also need to go back and debug this handwritten assembly code that basically no one except experts can read. So you find, comments in actual source code, even for reference implementations, that say something like, "Can this case really happen? I don't think so, but check." Or you can have experts write code in what was intended to be an extremely simple and readable implementation of a crypto library, and yet make a bug where they added the carry to the wrong variable. One was called R1, one was called R2. And yet you make a mistake like that, and suddenly the security property has been totally blown. And both of these were done by some of the most famous cryptographers alive. So this is not just an accident by some amateur doing the code. It just turns out that even for experts, debugging these and writing these is extremely difficult. Calvin, question?
A little comment is, as I read about this project, that fuzzes like tons of different crypto libraries against each other and tries to find bugs like this. But
there are projects that use fuzzing to try to find bugs like this in crypto libraries. Those papers are disappointingly successful. That said, fuzzing can't find certain classes of bugs. So for example, this paper actually mentions a bug in OpenSSL, which was due to some confusion about what the preconditions of a certain function deep in the code base was. And that bug would only happen for 1 out of every 10 to the 29th inputs. So you're probably not going to find that by fuzzing. In fact, it'd be very difficult to find it through almost any technique, except of course, actually complete verification. And of course, yes, complete verification, as we've seen throughout this class, it's expensive. You've all struggled to implement, to verify basic sorting algorithms, but at the same time, for something as essential as this, and also for something you're already probably paying potentially in the millions of dollars per year to an expert cryptographer to write, it might be worth doing this complete verification. It might still be cheaper given the impact that cryptography bugs can have. Other questions on crypto libraries, why it's important to verify them? Go ahead, Calvin.
I was also wondering like what the steps like verifying the MAC of a sender and like figuring out if like you have like the wrong key would like impact this, if you'd be able to like get rid of most passive bugs just be like the input not being valid.
The thing is, usually in a crypto library, you have to assume that the input is untrusted. So if you're a server, you are not just assuming that browsers connect to your server to, you know, do whatever business it is your service supports, but also potentially to just send you garbage to see how your server responds, maybe break it, maybe learn some secret value. So a lot of the like careful testing and MAC checking and all that stuff, that's there for security reasons, not for correctness of implementation reasons. Though, you know, in some sense, a sufficiently bad bug is a malicious attack. Okay, so we've talked about this general idea of cryptography. We talked about cryptography libraries. We've talked about what it takes to write one, and we've talked about how hard that is. And that's why this Fiat cryptography project exists. The vision is to have a correct by construction cryptography library, as in generate a cryptography library where, due to how you constructed the library, the proofs involved and also the techniques used, you could guarantee that there were no bugs. In other words, we'd like a method that produces verified cryptography libraries. And we'd like a method, not just a single cryptography library, because there are all these different algorithms and primes and machine combinations. So even if you wrote one verified cryptography library, it'd be obsolete by the time Intel introduced a new chip architecture or a new chip family. Or as soon as you wanted to port it, or as soon as for security reasons, we'd migrate it to a different class of elliptic curves. So how does Fiat do this? Well, basically speaking, Fiat traverses this long pipeline. At the top of the pipeline, you've got this general goal. You want to do private key exchange using that algorithm we discussed at the beginning, Diffie-Hellman key exchange. Then this goal is implemented via these mathematical principles of elliptic curves. So these principles provide a blueprint by which you can achieve private key exchange. These mathematical principles, they rely on a specific algorithm that you use for doing multiplication of points on a curve. And this algorithm is implemented by basically some high-level code for multiplication of large integers modulo a prime. And this high-level code is actually represented on your machine by some low-level assembly or C code that implements that high-level multiplication idea. So in Fiat crypto focuses on not all of these steps, but some of them. This top-level step, that's just decades of math that tells you how elliptic curves work, how multiplication elliptic curves works, why it's difficult to do various things that need to be difficult for this to be secure. From these mathematical principles, there's an algorithm for multiplication on a curve, and that's not part of the, I'm not sure if that's part of the Fiat crypto project. That might be part of the broader SSL library. But that algorithm for multiplication, that is implemented by this high-level code, and that high-level code is written and proven in a dependently typed language called Coq. It's French. You'll often see it pronounced Coq, or you'll see it pronounced Coq by Americans. It means rooster. So it's implemented and verified in this high-level language. That gives you high-level code. That high-level code uses things like heap allocated lists and linked list data structures and arbitrary size integers. So it's definitely inappropriate for actually running a crypto algorithm. But then that high-level code is converted into this low-level C code that implements that high-level idea using a technique called partial evaluation, which is really leveraging this idea that dependent types mix both computations and proofs in the same language. So let me talk about some of these in a little more detail. But before I do that, any questions about this kind of high level structure that we're doing here? Good. So why do we want to do this sort of big pipeline kind of approach? Well, basically, we can generate code like this. This is a square function for on a 32-bit architecture for doing, or maybe this is a 64-bit architecture. It looks 64-bit for the X25519 curve. And we can generate all of this curve, all of this code from the high-level properties that we've proven a single time, and then convert it into low-level code with a code generator that we can also verify correct. So what I mean by that is there's one piece of code called the code generator. That piece of code is proven correct once. Then there's one piece of high-level code, which is the multiplication algorithm. That's also proven correct once. And there's actually a couple of these multiplication algorithms, but they're each proven correct exactly once. And then it's turned into this low-level code automatically. So each of the different algorithms, which are implemented once, curves, which have to be specified once, and architectures, which have a simple description of the system, again, one description per architecture, each of those are separate in this system. So instead of having this n times m times k property, we instead have an n plus m plus k property. So this allows you to do significantly less work to do the implementation. And furthermore, of course, each of the n, the m, and the k are a lot simpler. For the architecture, you just need to describe what low-level operations are available in that architecture. For the curves, you just need to describe the prime and the curve structure used. And for the algorithms, you only need to describe some high-level ideas about how you might multiply multi-bit numbers. So this architecture, by splitting it up into sort of a higher level and lower level phases linked by a code generator, the advantage of this structure is that instead of having to verify dozens and dozens of crypto libraries, which are kind of repetitive, but all a little bit different, you verify these two admittedly more complex pieces of code once and automatically get new crypto systems produced by the structure that you know are correct. So the overall result, it's lower maintenance, it's more agile, you can generate novel crypto systems in not that long, and more importantly, without necessarily being an expert cryptographer. So let's take a look at some of the key sort of pieces that enable this to work. So first, let's look at this high level algorithm. And in particular, let's look at the algorithm for multiplying two integers, modulus and prime. That algorithm looks something like this. Here, this is again Coq code, so it's a little different from Lean that you've seen, but it's quite similar. This code defines a function. That function is called molmod. It takes place modulo some crypto system, which is represented here by n. It takes in two numbers, a and b, and those are represented by a list of arbitrary size integers related to this crypto system. And finally, it produces a number in that format as well. So already you can see that this code manipulates lists of arbitrary size integers. And as you might imagine, this can make it a lot easier to reason about than low-level assembly code. You can actually just multiply two numbers and not worry about overflow or underflow or carrying or any of that. And furthermore, the ability to manipulate arbitrary size data structures means that we can write this code in a simpler, clearer, higher level way. So in fact, if you look at this code, what it does is it first converts this list of coefficients into this weighted product representation. So the weights like 1 and 2 to the 23 are represented explicitly. So it converts A and B into that form in these two lines. Then it does multiplication of numbers in that form. And that is quite simple because you can do this just for all pairs in both lists. Then it groups like terms together. and then it converts this weighted product representation back into a list of coefficients. So this code is what you would write if you wanted an exceptionally clear description of how a crypto system works. And correspondingly, it's relatively easy to verify that this code is correct, where correctness, for example, means that if you convert the numbers that these tuples represent into actual integers and multiply them, you'd get the same result as applying this code. So it's exceptionally clear, but it then raises the question of how we can turn this code, which manipulates data structures and does what looks like all this wasteful work, back into something, you know, that you could write in assembly. You certainly wouldn't want to do all this. It'd involve memory management, which is a big no-no for constant time reasons, but it'd also just be a lot of wasted work. It'd be too slow. And so what you do is that you remember that in a dependently typed language like Lean or Coq, you have this ability to run computations as part of your proof. Remember that it's a language that mixes both computations of values and proofs in a single place. And it turns out that all of the list handling that your code does, that's statically known. Once you know what curve you are applying it to, once you know the prime modulus, you know how many digits are there going to be in the list of digits. And because of that, you know what exactly is my list of weighted product form going to look like. You know the coefficients in each place, you know the order of terms. You can track what gets multiplied by what. So in effect, what you want to do is you want to symbolically evaluate this high level code, given known parameters for the number of coefficients in the crypto system you're using. So you want to take this multiplication code. I don't know why I have the hiccups. You want to take this multiplication code, you want to statically evaluate it. And when you statically evaluate it, you'll get this code that applies to the concrete variables you've introduced, but erases all of the list handling and list structure code. Basically because the list structure is known statically, and the only things that aren't known statically are the operations on machine integers that you are doing. So this is basically leveraging that built-in computational procedure, the fact that you can run your dependently typed language as well as checking the proofs. And you're using that to automatically generate the low-level operations that you want to execute in your code. So questions about this idea of splitting the high level from the low level code, and then using partial evaluation to produce the low level code itself. And I should note, I asked Adam, and he said that this was the PI that was in charge of the work on this paper. And his take was that this was probably the biggest insight that made this work possible. So questions about this idea. If you don't understand it, it's a great thing to ask questions about.
I don't understand it, but I don't understand to the point where I don't really know what questions to ask.
What a great question. That is a fantastic question to ask, and it's a good thing to admit. So let me try to demonstrate a much simpler example than all this like multiplying modulo stuff. Let me open a new Lean instance and just begin a little, just show you a little bit what I mean by this partial evaluation idea. Okay, so in Lean, I can ask Lean to do some kind of computation. So I can, I need to tell it that this is Lean code. In Lean, I can say reduce 2 + 2, and the reduce command here asks Lean to run a computation. So I wrote 2 + 2, and Lean ran it, and it got 4. But in Lean, you could also have variables. So I can introduce variables x and y of type int. Can I not do that? Well, I can introduce a variable x and y of type int like this. And then I can also write down the expression x + y. And now Lean can't run it and get a number out because it doesn't know what x and y are. But it, keeps the expression around because you might want to write down something like x + y = 3. And this is actually just some proposition that you might be interested in. So when you write down this proposition, Lean will run both sides, but running x plus y doesn't do anything if x is unknown. Of course, if I give x a value, then Lean can actually run this, and now it is concretely inlined my definition of x so that it is concretely adding 4. And furthermore, if I go ahead and give a value to y as well, now you can see that, oh, I still got this equals 3 thing going on, sorry. Now you can see that Lean has fully computed this whole expression and told me that the result is 9. So that's what I mean by this idea that in Lean, you can both write down general computations like x plus 5, but you can also run computations. And so basically, it can do evaluation. If I give x and y concrete values, it can evaluate the result and give me an answer like 9. It can also not do evaluation if certain variables don't have values like x here. And so we call that partial evaluation. And what that means is that we can have a computation, part of which is known, part of which is unknown. So for example, Lean has lists built in and also an append function. So we can ask it, what happens if we append xy to yx? And you can see here that we haven't told Lean what x and y are. X and y are still defined just as generic variables of their type. But we have concretely given it the structure of the list itself. Lean knows that this is a list of 2 elements, x, y. So because Lean knows the structure of these 2 lists, it knows how to append the 2 values together, even though x and y themselves are unknown. And we can also go ahead and we can write a function like we can write list add. So I'm going to write list add to take 2 lists of natural numbers and add them point by point. And I'm going to define it by saying if I add an empty list to anything, I get the empty list. And if I add, this is the empty list as well. But if I add 2 lists of the same length, I want to produce A plus B sorry, too much Haskell recently. So now I've defined my own user-defined function. And if we think of these lists as lists of coefficients, then you can even see how this is, adding 2 multi-digit numbers. And now I can ask reduce list add x, y, y, x. Of course, these are ints. And you can see that Lean has gone ahead and computed each element of the resulting list as best it can. So the whole list manipulation code that we've done here, where it checks whether the list is constant or nil, it enforces some kind of same length property, etc. All of that is now gone. Lean can compute that away because it's statically known, while leaving operations about x and y in place. Does that make a little more sense, Skylar, about what we're trying to do here?
Yeah, that explains it. Thanks.
Excellent. Oliver?
My question is, what is the distinguishing feature between dependently typed languages and other languages that makes this partial evaluation possible? And can you do partial evaluation with non-dependently typed languages?
Oh, totally. Partial evaluation is necessary to do dependently typed stuff because basically if I write a if I have a vector, if I have a list and I have a proof that the list is length 4, I want that proof to be a valid proof that it is a list of length 2 plus 2. And if I have a list of length x plus 4, I want that to also be known to be a list of length x plus 2 plus 2. So this kind of partial evaluation, it's something that dependently typed languages generally have. There's not in principle any reason you couldn't write a partial evaluator for even an untyped language like Scheme. It'd be fine. It'll probably be a little harder, but you could.
I see. Thank you.
Okay, so I want to talk a little bit more about a few other features that came up in fiat cryptography, but I did want to explain this partial evaluation idea because it's a key strength of proofs in this style. You know, in Daphne, for example, this stuff wouldn't work. This isn't a part of how Daphne views the world or the weakest precondition generation idea that many of you have been implementing, absent from there. And it allows you to automatically go from this high level code with all sorts of data structures and niceties down to low level code. Now, as you saw just in that lean example, we still have high level integers. These are arbitrary size integers. So to turn this integer arithmetic into low level machine arithmetic, there's an additional step, bounds inference or size inference, which is that we want to replace these arbitrary size integers with machine integers by learning how big can those integers be. And to do that, fiat cryptography applies abstract interpretation, the same technique that we studied earlier in this course. And that abstract interpretation is going to go through and using the ranges you know for each of the input variables, it is going to automatically compute a number of bits necessary to represent each of the outputs. So it does that in kind of a standard way. It has these transfer functions for each of the mathematical operations like to, output, multiplication with carry. It implements a transfer function for each of those. And because those functions are implemented in a dependently typed language, it not only implements those functions, but also proves them to be correct. If you recall, when we talked about abstract interpretation in class, I showed you what you'd need to prove in Daphne in that case for it to be correct. Because the transfer functions and the lattice and all the other aspects of this abstract interpretation are proven correct in Coq, you know that it produces valid output. And as a result, you know that if it allocates a 32-bit integer to somewhere, there isn't going to be any kind of overflow or carry that you didn't handle that would be necessary to implement that correctly. So that analysis, there's one trick that I thought was really cool that I wanted to highlight from this paper. Sometimes fast code has to use these hard to analyze tricks. So for example, in crypto code, it's quite common to replace this 3-term product with this more complicated piece of code. The advantage that you're replacing 2 adds and 3 multiplies with 3 adds and 2 multiplies, multiplies being a lot slower than adds. And unfortunately, analyzing this result using abstract interpretation is tougher than analyzing the input because you have to track the dependency between the A and D terms here and the AD term here. You want to keep track that there's some cancellation going on. So what they do in fiat crypto is they actually write both expressions in the code using this construct they call equivalently. And the idea is that the analyzer uses the first construct, which is easy to analyze. The implementation uses the second construct, which is faster to run. And there's a side condition that they have to prove, which is that those 2 expressions are equal for all possible inputs. So this is kind of a neat trick that they use for writing code that they can simultaneously analyze easily, but also yields fast code when run. So let's tell you a little bit, now that we've sort of dived into some of the details of how this worked, let me tell you a little bit about how this has ended up being used. The code is about 38,000 lines of code. You can find it on GitHub. I think it's called Fiat Crypto on GitHub. And you can look through all of the code, including some of the demo code, which is particularly handy if you want to get some sense of what's going on. So if you've used Coq before, you can open this up in Coq Guide or in Proof General, and you could step through the implementation. those 38,000 lines, which include a lot of like boring proofs about number theory and bitwise arithmetic and that sort of thing, that code will automatically generate C code for different architectures as you specify them. And you can add new prime numbers to the generator very easily. Basically, you just need to describe the prime in this simple structure. In fact, the code requires so little code to generate a new crypto implementation that the authors scraped a bunch of suggested primes from a crypto mailing list. They got 80 different primes. Most of these probably had never been implemented in a crypto system before because it used to take so much effort to generate a cryptography library that, you know, some random person having an idea on a mailing list is not enough. They were able to generate an implementation for each of these primes, time the results, and you know, this is the sort of experiment that would be totally impossible without the automated approach. As far as I know, the primes that we use today are in fact some of the best ones. They didn't like uncover hidden gems, but nonetheless, this is a cool example of how automation lets you do things you could never have done before. And as you can imagine, this would also make just experimentation a lot easier. So that's the state of the code right now. It is used widely. In particular, it's used by this library called Boring SSL, which is a branch of OpenSSL maintained by Google with the intention that it is more boring and thus in some sense more trustworthy. The key thing is that this means that this verified cryptography library is used for the crypto implementations of P256 and X25519 in Chrome, which is by far the most widely used browser. So that means that something like 50% of all internet connections across the entire world are running this verified code. And if you're talking to Google, if your connection is to Google, you're running this code on both sides of the connection. Not only that, not only is this code verified, so you know it's bug free, it's also a lot easier to maintain. It generated faster code than existed in the project before. In one case, it generated 32-bit specialized 32-bit code, whereas no code for 32 bits existed at all because it was seen as too tedious to write. And it also allowed them to experiment with a bunch of new optimizations that they'd hypothesized, but just it was too tedious to implement them when the stuff you're modifying is hand-coded assembler. But because it's been replaced by this generated code, it's a lot faster and of course known to be bug-free as well. So on that speed question, here are some numeric results. This is specifically, I think, for P256, not 100%. No. I think this is X25519 results, but you can see the paper for both tables. This is just a screenshot of the paper. Here is the paper results in question. It generated some C code, and then they had some simple tweaks to the code that made it significantly faster. This tweaked C code is almost as fast as the fastest known C implementation. You can see that they differ by what, like half a percent? No, by 5% in speed. It is also fairly competitive with the fastest known hand-coded assembly implementations. So in Fiat, they don't actually generate assembly directly. They generate C and rely on the C compiler to generate the assembly. And in some ways, that's suboptimal. You could do slightly better if you had hand-tuned assembly, but this code comes quite close. And it comes quite close with these additional benefits to maintainability, to experimentation, and of course, to bug freedom. And in fact, the paper points out that some of these other implementations have had known bugs in the past. So this idea of these crypto implementations having bugs, even these specific ones, is not a purely theoretical concern. So questions about these sort of, about the results here, this project, any thoughts you have? You're using this code right now, whether you like it or not. Hope you like it. Oliver?
So I'm amazed it beat OpenSSL. Do you know any reason for why they beat it by so much?
Well, OpenSSL, see, here's the thing. OpenSSL is by far the most important crypto library in the world because so many things rely on it. That means that they are a little hesitant to accept patches from just, who knows what, containing,
I see.
random implementation. So I believe this is actually the assembly code used by OpenSSL for this particular architecture. But OpenSSL also has some C code, and that C code is not as well optimized just because it is
Oh, I
so
see.
darn hard to write.
It's less specific to the architecture.
Yes. Skylar?
Why is OpenSSL so important?
Because it's free and almost everyone uses it.
Okay.
Basically all cryptography by any non-Windows machine uses OpenSSL. And non-Windows machines are the vast majority of servers out there on the internet.
Makes sense.
If y'all remember Heartbleed, when there was a crypto bug that hit major newspapers, that was a bug in OpenSSL. It was such a big deal, specifically because OpenSSL is used everywhere. Kelvin, did you have a question as well?
Yeah. So this was a generated C code, but I remember you saying that it was generated for particular architectures. Is this like C that uses compiler intrinsics for 64-bit computers, or?
Yeah, great question. So the architecture specific stuff that comes in here is actually some higher level concerns, like how exactly do you represent numbers? If you look at the paper, it'll explain that you don't necessarily want to represent your 256-bit number as x0 plus 2 to the 64 times x1 plus ... You might want to represent it as x0 plus 2 to the 51 times x1 plus ... So those those choices in sort of high level algorithm, those are driven by the particulars of the architecture. How fast is it at carries? How fast is it at two output multiplications? That kind of thing.
Yeah, just know in general that C tries to be more architecture agnostic and doesn't even define the number of bits in certain number types. So I was wondering if it'd be easier to just generate assembly at that point.
Well, the paper does point out that this is not normal person C code either, right? It's mostly this extremely long list of bitwise operations. So what does this ask the compiler to do? Register allocation and instruction selection. Register allocation meaning which values to compute when, to use all of the available fast memory on the machine. Instruction selection to mean how do you pick the specific instruction that is going to be fastest for treating carries or multiplies in this particular architecture. And Adam has some other presentations on this idea. Where he's talked about some of the limitations of using C code. So for example, C compilers tend to be really bad at handling carries. Anyway, the point is that, yeah, they probably could generate assembly, but it was easier to generate C, it's higher level, and it's, there's still a significant verification effort going on just to write down what do C instructions do, etc. Translating that to assembly, it wouldn't be that much harder, but there'd be more moving pieces, and I think just for this project, that trade-off didn't seem worth it. They are, in fact, working on some improvements to this code. So one, they're working on speeding up code generation. They've got examples of specific specific operations that take weeks to build. So there's one of Adam's grad students is working on big changes to some of how the core of Coq works that will speed this process up. That's sort of looking at this partial evaluation step. And they're also working on backends. And one of those backends includes this programming language that Adam's group has developed in Coq over the years called Bedrock, which compiles directly to assembly and is also verified. So, for one, it means that bugs in your server won't result in insecure code. And for another, it means that they would have more control over the assembly being outputted, and potentially they could make it faster that way as well. Any other questions? Actually, given the time, I'll ask you to hold any additional questions. I just want to say that our next lecture will be our last. There is a course feedback form posted for this lecture, so please fill it out. Tell me what you thought about, we'll basically ask you which part of the class was most interesting along the side, the ordinary questions of how useful and clear this lecture was. And then you have the final presentations due tonight before midnight, and the final project uploads due Tuesday. I will also be emailing you about leaving questions on others' presentations and answering those questions. So just keep abreast of the final project stuff going on, and I will see you for our last lecture on Tuesday, where we'll sort of do an overview of the course, talk about what we've learned, and give some thoughts about software verification going forward. So hope to see you all on Tuesday. And if you had any further questions, you can ask them now. Otherwise, you're free to leave. See you in 5 days. Hachan, go ahead.
I think the feedback is not up yet on the cross website.
It's not, huh? Okay, let me take a look at that. I must have forgotten to publish it or something. Stay on the line. I will make it public, and then you could fill it out. I see a lecture 27 feedback on Canvas that you should be able to fill. Oh, I see. You mean that I haven't published it to the course website? That may well be the case. It should be up in a minute or two once it finishes uploading. Any other questions? I mean, if there aren't questions, y'all can go. But I'm happy to answer any additional questions about any of this material, anything you thought was interesting, anything you wanted to know about the paper, if there's something that you didn't understand in what you read.
I have a small question about my project evaluation thing.
Oh, okay, sure.
Yeah, so like, how are you going to evaluate my project? Because my project is sort of similar to the alternative assignment, but it's also a group project. So like, do I come up with my own evaluation, or like, do you want to see a lot of test cases and my code working on all of them, or?
That's a good question. I think I can kill the